My name's Matt. I'm a DSP engineer at Focusrite, and I'm joined today by my colleague Andy. And Andy is a firmware and hardware engineer at Focusrite. Andy and I have worked together on all sorts of Novation products in the past. So that's where we've come from. Today we're going to talk about embedded software development and the wild ride that it entails. You're probably well aware that this conference started life as the Juice conference, and it was always very plugin centric. And increasingly over the years, it's come to include hardware development as well, which is the angle that we come from. So we thought it'd be interesting to give an overview of what it means to be developing embedded software and what kind of issues are you going to encounter when you take your great idea and try and stick it in a piece of silicon, load it into a box, and ship it around the world. Let's get started with some definitions then. Embedded devices. I'm sure everyone's aware of what an embedded system is, right? It's a microwave or it's a washing machine. For us, it looks like a little red box with some lights and some knobs and some buttons on it and some audio processing. It's notably not a computer, but inside it there are processors. And yeah, stick it in a box and send it around the world. Running on these devices is firmware. And the difference between firmware and software, we can argue about it later if you fancy, but it's harder than software, softer than hardware. And for us, the important thing it provides is abstraction. We use firmware to abstract away all of the aspects of the processor that you need to bring it up from this being a useless pile of transistors into something that can be used from high-level software. So we define a hardware abstraction layer. Looks a lot like an API, and this defines how software can access file systems or USB or MIDI or all the stuff that's processor specific and you need to care about the implementation. This firmware will be running on processors which are not your typical processor. For us, they're microcontrollers, and in fact, in a device, you might be using more than one. Microcontrollers are distinct to microprocessors in that they are typically much more responsive, and they're designed specifically for real-world interaction and control. So you'll use them to drive electric circuits, to monitor circuits, to drive motors sometimes. They're designed to be responsive, and it's very, very reactive and good for controlling real systems. On them, you won't typically run a rich operating system, so you won't find something like Linux or Windows running on a microcontroller. Part of the reason for this is you don't really have enough memory. Also, you don't have an MMU. This is the thing you'd normally use for translating physical or logical to physical memory addresses. On a microcontroller, all the memory you have is physical memory. So the addresses you're using are physical addresses. That's only, well, we still need operating systems, right? So if we can't run Linux, we'll run something else. And we'll use a real-time operating system. At Focusrite, we're particularly keen on FreeRTOS. FreeRTOS is nice because it's minimal, and it gives us that subset of operating features we need to get something off the ground and working as quickly as possible. So you have tasks or threads. You'll have some synchronization primitives, like your mutexes, your semaphores, and a set of devices for inter-process communication, like mailboxes. Another reason microcontrollers can be particularly responsive is the immediacy of the memory. On a fancy microprocessor for a desktop, you'll be well aware you have layers of cache, like L1, L2, L3 cache, and this gets successively faster as you get closer to the core. We need cache really because the processors are so quick and so complex now that it's hard to keep them fed, so you need to have at least some memory that's fast and close to the core. Microcontrollers are a lot more straightforward. You're not going to get fancy features like multi-issue or out-of-order execution or branch prediction, which is a bit of a mixed blessing because it means an Novation circuit's never going to be vulnerable to a Spectre or Meltdown side channel attack. But yeah, they're not quite as clever and a bit more simple. All the memory it needs can be considered like L1 memory, and it's right there on the chip. Since it is right there on the chip, that hints at another key issue you'll have with embedded systems development, which is there's just not a lot of memory. On your typical microcontroller, you'll probably have a few hundred kilobytes of RAM, and that's not much at all. Like a microprocessor, you can go off-chip if you want more. So on a desktop, you'd hook up some nice DDR4 RAM and PCIe hard drive. It's not really possible with a microcontroller. Like your RAM is probably going to be accessed over standard SD-RAM. You'll have a flash memory that you might be able to access over SPI, but it's going to be a lot slower, so you're really dependent on what's on the chip, and there's not much of it. It's a similar story with flash. Flash memory, you're probably going to have a few hundred kilobytes on the device, if you have any at all. It's not uncommon for simple microcontrollers to have no flash memory, that's non-volatile memory, and just have to go off chip. Now, programming is harder, I assure you, when you don't have much memory. This on screen is a memory map, and that's for an STM32 microcontroller. The memory map becomes very, very important. This shows you all the different areas of physical memory available to you on the chip and what they're used for. So some of that will be used for configuration or setting registers. Some of it will be areas of RAM you can access. And it's not necessarily contiguous. So it may be that there'll be one bit of memory over here you can use, and another bit of memory you can use over there, but it's not in a continuous address space, so you can't just have one big, huge buffer. As a firmware engineer, you spend a lot of time staring at the linker map, wondering why you chose this profession. But also, you work in linker scripts, so you'll be very, very careful about how you use the memory. The linker script tells the linker where this stuff is, how it can be used. And then the linker map, it gets spat out by your linker that tells you what you're using for what, which bit of your system, which bit of your binary is using how much memory. That's important for figuring out afterwards like, what you did that suddenly consumed all of your RAM. As programmers, we're pretty hardwired to think about computational complexity in terms of processing time. Like when somebody says, like, what's the big O of this algorithm, you're immediately thinking about the kind of processing cycles it will consume. In embedded, a larger concern is probably memory complexity. Because you can write the fastest algorithm in the world, but if it doesn't fit on your micro, it's absolutely useless to you. And memory becomes a much bigger concern. It's not just memory. As a desktop developer, you can probably be fairly confident targeting maybe a couple of instruction sets, a couple of operating systems. I'll give you fairly good coverage. For embedded, there's a huge range of devices you could be working on. And often you could be working on radically different microcontrollers inside the same product. And these can differ in some pretty fundamental ways. They could have different word sizes. So you could have an 8-bit micro, or 16-bit, or 32-bit. You could have different memory architectures, which radically impacts the efficiency with which your algorithms can run. Then everything else, you can have different clock speeds, different instruction sets, different peripheral sets, memory sizes, different vendor families, different packages. There's a huge array of devices you can be choosing from. And so picking the right devices is really key to getting a good start in the project.
So I'm going to take you through how we get from that somewhat overwhelming set of choices and variables that go into choosing a microcontroller towards a platform that we can build the product on. The electronics hardware design really drives all the choices we've got to make here. That defines what we need out of the microcontroller. So we'll start there. We'll start at the beginning of this process working really closely with the electronics team, figuring out how to take the set of product requirements, what's the user actually going to experience, and turn that into a specification for the hardware design. And the microcontroller sits at the core of that. So we'll start to build up a picture with the electronics engineer of what's going to be in the system. What other devices are going to be around the microcontroller? What's the microcontroller going to have to talk to? What protocols are we talking? How fast are we moving? What data have we got to ship around the system, at what interval, at what frequency? If we've got things like MIDI and USB connectors on the back, then we're going to need transceivers inside the box for those, and we're going to need to communicate with those in some way. If we've got an audio system on board, how are we going to get data in and out of that? And how are we going to control things like mic preamps and converters that are in the system too? If we've got DSP or Bluetooth audio on board, who's even doing that? Is that going to happen inside the microcontroller, or are we going to ship that off to some dedicated subsystem? And how are we going to control that subsystem and get it a firmware update? So we start to build up this picture of what the whole system's going to look like, what the microcontroller is going to have to interface with. And when we get to the end of that process, working on that with the electronics engineer, we kind of have a shopping list for what we need out of the microcontroller. So we can look at this huge market of different devices and start to think about where we fit in that market. We're looking for a part with the right combination of peripherals, the right amount of flash, the right amount of RAM, thinking about whether we need all the features of something like a Cortex-M7 or whether something simpler and lower cost like a Cortex-M0 could do the job. often start this journey of selecting a specific part, thinking about the vendor that we're going to buy the microcontroller from. And that might seem like a strange place to begin. You might think, if we can write code for one Cortex M4, why can't we just run that code on any Cortex M4 and buy whatever's cheapest or most available at the time we're building the product? But in actual fact, the implementation of the peripherals can be quite different from one vendor to another. So if we've developed a load of prior art and experience with a particular vendor's implementations, then it can be a whole thing to start using somebody else's implementation. We can run into all kinds of unexpected issues. So we're taking some risk there. We'd want to have a good reason to make that change. Once we've chosen where we're starting with the vendor, we'll start to think about what family we're going to work with. And just to give you an idea of the range of devices that's available, each of these yellow blocks is a whole family of microcontrollers available from ST, just in their 32-bit range. So we're going right from really small devices that are just at a couple of tens of megahertz down at the bottom, up to a few hundred megahertz that probably could run Linux, I guess. I've had desktop computers that are worse than that. Each of those families is targeted at a particular kind of application. Maybe it's a low-power device that is intended to spend most of its time asleep and has lots of capability to wake up from interrupts. Or maybe it's a high-performance device that has quite a lot of onboard RAM and is really just dedicated to crunching numbers as quickly as possible. We're going to position ourselves somewhere. We're going to choose this F4 family at the top and the high performance because we're fancy. And we'll zoom in on that and start again. And we have the whole range again. We have a huge selection within this. Each of these lines is a specific device. And you can see we've got a broad set of peripherals that are available within this family. But there's still quite a lot of variation. We can go from quite simple devices that only have a few peripherals up to higher end devices that have got dedicated peripherals for interfacing with a TFT or something like that. We'll pick our specific device that we're going to use with the right amount of flash and the right amount of RAM and all that stuff, and maybe a backup option in our back pocket in case things don't go quite how we expect. And then we can start to think about how we're going to set the device up. This is a typical kind of block diagram that you'd get when you start looking at a specific microcontroller. So we've got the core at the top, we've got the memories around the core, and then all the way down the side is a ton of different peripherals that are available. And the thing to notice here, the tricky bit, is that there is more than one instance of most of the peripherals. There's multiple timers, there's multiple serial interfaces and all that stuff. And the catch is that they're not all the same. We can't just choose one and swap it for the other. They all have their own specific features. They all work in a slightly different way. So we need to get to know each of them and figure out who's going to be right for which job in that block diagram that we drew. This is a job of getting into data sheets and reference manuals and example code and figuring out exactly where the little links in between peripherals are going to lie that we can take advantage of and come up with our magic efficient system. You start to feel like a Dan Brown hero, like rifling through historic text in a big library, except we're not deciphering runes to save the world most of the time. We're just trying to make synths sound good, but that's good too. The kind of catches we're going to run into here, right? If you need a specific mode of operation to interface with a converter that you've chosen, say, that might only be available on one of the serial peripherals, so we might have to choose that one and build everything else around it. There may be useful links in between the peripherals that we can take advantage of. Instead of having a timer, trigger an interrupt, and then we service that and trigger an ADC sample, and then we can interrupt when it's done, and we copy that sample out of the peripheral into memory. If we're smart at this point, we can spot that timer 3 can trigger ADC1 directly, and then the DMA peripheral can talk to ADC1 directly and copy that out of the peripheral into memory for us, and the core didn't even have to wake up. There can also be links between the peripherals that are less useful. There's normally shared resources. There are normally not as many interrupts available as there are peripherals or events from peripherals. So there will be times when if we happen to pick a particular timer in a particular SPI, they'll share an interrupt. If we want to use both of those bits of functionality, then when that interrupt triggers, before we can even start servicing it, we have to figure out what it is, what actually caused the event that we're servicing here. The reality of this is lots of tables, lots of building up spreadsheets and figuring out the catches in the system, where we think things might go wrong. It's normally data that comes from a few different sources, so we have to do a lot of that, pulling things together ourselves and looking at prior art. Sometimes you get a fancy tool from the vendor, like this one in the bottom right, where you tell it what you want and it gives you some choices, but you still have to get into the nitty-gritty, really, of how the microcontroller works. Each of those bits gives you a different piece of the puzzle, and then eventually things come together. And we have a game plan. Yeah. Once we've got that game plan, we're confident it will definitely probably work most of the time, but it's a complicated system. Things are going to go a little differently to how we expect. And the earlier that we can find those problems, the more flexible we are. We can just change our microcontroller. We can choose a different set of peripherals. We can change the pin out. We're still working closely with the electronics team. They haven't done any big work yet. So we want to do some work now to do some sense checking of those things, to validate those assumptions before we get too deep into this choice of microcontroller and the configuration. We're going to think about where are we pushing the limits of the microcontroller? Where are we going to burn all our CPU cycles? What about those RAM estimates that we made? Could we be a couple of 100 bytes out, or is it possible that we might find a few 50 kilobyte buffers that we just can't even fit in the RAM? We've got a new converter that we want to use. We haven't used it before. I've looked at the data sheet. I think the data format matches the I2S peripheral in this specific mode, but no one's ever actually seen it happen, and that's not true until it happens. So we want to come up with some system that can allow us to do some experiments around what we think these risks are. And we will do that through what we call a Frankenstein, where we'll get just enough hardware to let us answer those questions. The Frankenstein might be a dedicated board. This is how Novation Peak started out, where we built probably our most complex Frankenstein, where we had the FPGA and all the analog circuits around it. It's basically a Peak on one board. Or we might be able to get away with something like this at the top, where we just have a couple of dev boards, we find samples that we need, stick them on a bit of breadboard and wire things in and make a bit of a glorious mess like that. It's all about doing something that we can move quickly with, just gets us the answers that we want. We don't care about the form of it or even being feature complete at this point. That can give us the confidence that we need to get onto a fully fledged prototype. We're making pragmatic choices at this point as well about the tools that we're using and the way we write the code. The vendor will give us some tools. We'll probably start out with those so that we can have an easy discussion with the vendor when we find problems. They'll give us example code as well, and we have to strike a bit of a balance there between just hacking that example code into something that represents our functionality and calling it a day versus doing something a bit more deliberate in terms of design. Because if this works well, then this will quickly start to become the beginning of production development.
Right, so Frankenstein is alive in some form, or Frankenstein's monster is alive. It's time to start some project development in anger. At Focusrite, we form cross-disciplinary teams. So in a typical development team, you'll have firmware engineer, software engineer, hardware engineer, maybe a DSP engineer, depending on what you're working on, and possibly most importantly, a QA engineer. Anyone that's done any kind of Agile or Scrum will recognize what we do. It's a fairly typical arrangement. QA engineers are involved in the project right from the very beginning. So they'll become very, very familiar with the spec. And in many cases, they can come to know the product kind of better than anyone else. This means they can be very, very aware very early on of what areas of the product are likely to be the most complicated, what things are likely to go wrong, and where do we need to push in additional testing. This could be testing for production, or it could be testing for development. Either way, getting awareness as soon as possible of where that complexity is can be very, very helpful. That information gets fed back to the firmware engineer, and as early as possible in the project, the firmware engineer will be developing tests. The firmware engineer's got a bit of an interesting position inside these teams because they're sort of the hub that's connected to everyone else. You'll be talking to QA about testing. You'll be working with the DSP engineer on where that code goes and how it runs and you know, how it needs to take over the whole system and have the highest priority ever. And they'll need to work with hardware quite closely. And it puts you in a challenging position because at all times you kind of have these different pulls and different influences from different areas. Despite that, they do have to work particularly closely with software and hardware. Hardware can be a bit different for us. Hardware tends to look a little bit more waterfall-y. We'll have periodic drops of new hardware during development. This is because as the boards develop, we move away from the Frankenstein and get something that looks closer and closer like the board we'll want to ship. We'll be identifying problems, maybe fixing signal integrity issues, maybe a few connectors back to front. Loads of stuff can go wrong. So we keep getting new updates of boards, and when these arrive, big box plonked on the desk of the firmware engineer. And the firmware engineer has to step aside and bring the board up. This means checking everything is as it should be, checking the power supply is sane before you even power it up, checking it can do everything it did before, and then checking any fixes are good. So if you fix something for signal integrity, has that problem gone away? Have you just played whack-a-mole and created a new problem somewhere else? This means the firmware engineer periodically stepping away from a typical sprint cycle to go and do some bring-up work. At the same time, the firmware engineer is quite tightly bound to software engineering. Just by the nature of the abstraction that firmware provides, the software engineers will be calling into the hardware abstraction layer and will be expecting something to implement it underneath. This can cause problems when you're sprinting, because if you start a software team up in an abstracted sense and allow them to work as fast as they can, and maybe in a couple of sprints they'll have a feature ready that wants to be driving pads, listening to pots, listening to buttons, and being meaningful and responsive. Meanwhile, 2 sprints in, the firmware engineer is still trying to figure out why the clock tree isn't working properly. To decouple the teams, we'll often use surface simulators, and that's what this is on the screen. This is circuit drums, which isn't a thing, it became circuit rhythm. These surface simulators are typically written in Qt or Juice, and they provide a software-based implementation of the firmware abstraction layer. So this can run on desktop, and when the software runs, it calls through the abstraction layer and is executing code in the surface simulation instead of the real hardware. The great thing, it means software can sort of progress at its own rate without having to worry about how well the hardware's working or if a few of the LEDs don't work. It can lead to some challenges, though. There's a real risk of a kind of big bang integration event where at the end of a project, the software is complete and the firmware is complete, and then you stick the software on the firmware and you run out of RAM. Or you run out of clock cycles, or something doesn't work as you expected, doesn't go well. You really don't want to find that out a few weeks before you ship. Bad times. To prevent that, we'll try and have more regular integration cycles. As quickly and as soon as possible, we're trying to get the real software running on the real firmware, running on the real hardware. Like sprinting, having Scrum leads to this happening quite intuitively, because every demo, people are desperate to show stuff on the hardware. Like you want to be holding the thing and pressing the buttons and showing it working. It's really exciting. So as soon as possible and as often as possible during those sprints, we'll try and have things running on the real hardware. That means any problems that happen, any disagreements about memory management happen very early and at a stage where it's still possible to deal with them. To get this kind of concurrent development working in a meaningful way, it means spending a little bit of time investing in tool chains that work for everyone. This can't just be a tool chain that works for some old Windows system using weird embedded tools that nobody but firmware engineers understands. It has to be something that can be used equally easily by hardware, firmware, and software engineers.
Thanks. So if we want that frequent integration, we've got to distribute tools around the team that allow people who aren't firmware engineers to still cross-compile for the target, to validate that their code does what they think it does, and debug it if it doesn't. There's a whole other talk here in doing this well. We're certainly still figuring it out. But our ideal that we're heading towards is cross-platform tools, ideally things that can run in a container, because then we can wrap up all the different stack of little tools that make the system work with their configuration scripts and files, and ship that around the team without people having to really understand it very much, or push out updates when we find problems on one person's setup without them even having to become aware of that. We can choose the tools that we're using in our stack according to that ideal sometimes. The options that we have available for different tools really depends a lot on the target that we're developing for. If we've got something with a large ecosystem like the Cortex-M, it's quite mature, then we get choices of the tools that come from the vendor, or proprietary tools, or maybe open source projects, and we can pick the ones that fit our needs the best. If we're using something more esoteric, like the XMOS microcontrollers that we use in a lot of our audio interfaces, then we kind of just have to go with what the vendor provides us and make the best of it. That containerization and the abstraction away from the desktop OS is always in tension a little bit with the need to get access to the hardware. That's the reason we're doing this in the first place. We can use things like USB IP to jump over that gap, but that's where the platform-specific implementations come in on the host side there. So there's always some work to do in wrapping those up and making that as easy an experience as it can be for different developers. But there's some problems involved in it, but it is totally worth it. We're finding already that it's so much more valuable to be able to say, just spin up this container, run this couple of scripts, and you'll be able to build the project that you didn't understand the toolchain for 5 minutes ago. It lets more people in the team work close to the hardware, lets us bring in specialists from other teams to work on a problem without having to have like 2 days of setup to make it worth getting them involved. And it kind of does work. Here's us in peaceful harmony after days of a seamless debug experience. We're still working on it. The purpose of all these tools is all about getting a window into what's going on in the hardware. So we have debug and trace tools to help us do that. But you can learn a lot from just having a couple of spare pins to toggle at different points in the execution. Maybe we can print to a serial port, and that can be all we need to get us some basic profiling. The step above that is that we can have a dedicated debug port, and we'll pretty normally do this on our hardware. There's a slight compromise here because it's a dedicated transport for debug. We can't run that over any of the customer-facing interfaces outside the unit, so we have to have some pins dedicated to that. It's normally only 3, 4, 5, it's not a big deal. And then we can run some GDB fork on top of that, get normal kind of GDB features with some plugins to give us context for the peripherals that we've got on the target and the OS that we're using. There's some traps involved in that debug access. You can get catches to fall into, I guess, with pausing execution on a real-time system like this. If we set a breakpoint, but we have real-time interfaces dealing with USB and network links and stuff like that, we'll time out, we might make the problem go away or might cause new problems that stop us seeing the problem we're trying to debug. Something as simple as if we're strobing LEDs, if you pause in the wrong place, all your LEDs are on full power, you can't see anymore, and the power system's clapped out because it was never designed for pulling that much current in one go. We can go more advanced than that. We can get into some really advanced debug access that requires lots more pins, lots of high-speed signals, very expensive debug probes. But as we go more and more advanced with that access, there's more catches. So we don't use this all the time. We just pull it out of the drawer when we've got a gnarly problem to solve. Things get more physically invasive with the pin out and stuff. And you need support for each of these debug features in the silicon as well. So on a capable system, that might be OK. If we've got a low-cost Cortex-M 0 microcontroller or something like that, it might just not have the silicon support for these kind of fancy debug features. We might just have to go with the toggling pins and serial debugging. There's also some work that we do during the project to provide access in a really, really non-invasive way for people like our product QA teams or for factory test. For that, we need to use a transport that already exists on the product. We normally end up using something over USB or MIDI. And that's all about giving those teams and those tests some way to trigger things on the hardware that are difficult to automate, normally have to be done manually. So that's things like triggering or faking button presses, setting controller positions, reading back gains and stuff like that from the hardware. In the past, we have tried to write some of those tests on the hardware and trigger a factory test mode, but what we tend to do now is to treat that as an API, set a kind of simple get and set routines for the access that those teams need, provide a firmware update method, and then those teams have what they need to incrementally develop those tests. We can get out of the way, and they can continue to make those tests more efficient, get better coverage, focus in on the bits of the system that really matter, and maybe throttle back on the areas where we're never seeing failures, and we can optimize the test time, speed up production.
Nice. As soon as possible, we need to be running firmware updates. So I have a question. Who here has written a bootloader? I'm sorry. Sorry, Ben?
It's fun.
It's fun. Writing bootloaders is fun.
Fun.
Does anyone agree with Ben?
Yeah, I'll go with that.
Yeah? Impressive. Cool. I find it terrifying. Yeah. OK. My opinion of bootloader is like the scariest thing that a firmware engineer will ever develop. And for really upgrading, for running firmware upgrades, it's essential. We want to get it running as soon as possible. We'll often use it during development. It's nice to do a bit of dog fooding with the firmware upgrader and make sure it gets as many flying hours as possible. It's that little blob of firmware that is as atomic as possible, you never want to change, and it just has to always be there and always bring the device up from its kind of useless bag of transistor state into something we can use. It will typically have some view of a firmware binary, and when you want to upgrade, it will replace them and then know that the replacement has been completed successfully. So if a firmware upgrade fails, the bootloader should observe this, and it should be able to fall back to an earlier version. The transport we use for firmware upgrade really depends on what makes sense for the product. So for Focusrite devices, we'll do it through Focusrite control over USB. For Novation, we'll use SysX. So this is Novation Components. This is our web-based patch management, firmware update management system. Having Novation Components and firmware upgrade effectively in the cloud is a great thing because it means the latest firmware is already there. So you don't need to send a customer to the website to download a new version of something every time the new firmware comes out. They're naturally here, managing their patches. They observe some cool new features are available. You hit the button, you get the new firmware. Under the hood of Novation Components, we're running Web MIDI and then tunneling SysX over that. Web MIDI is kind of cool because it allows us to use SysX, but in a modern framework. And we're really keen on SysX and Novation because it makes sense for Novation as a synth company. But it also means that if Web MIDI disappears, if Chrome disappears, in 50 years' time, as long as you have something that can still play SysX at your device, you can still control the firmware. I'm pretty sure MIDIOX will still be here in 100 years' time. So you'll still be able to control your firmware and perform upgrades. Yeah.
Okay, so because we're writing software to run at quite a low level in the system, and it's quite dependent on how the hardware is actually operating in real time. So we have to deal with the differences between the ideal operation that we pictured when we designed our system and the messier reality that we start to get into when we see the thing working. But this is the fun bit. This is where we get the awkward problem solving, the weird interactions between the hardware and the firmware that are always a bit different to what we think. It's where we get our battle stories. We can have problems with environmental noise coming from outside the unit or sometimes generated inside the unit. A typical one of that is getting pickup on ADCs that are monitoring the voltage that comes out of a pot. And we can think that's fine in the early stage of a product, and then when we put a plastic front panel on top of it and we need to turn the LEDs up a little bit so they can shine through that plastic, and suddenly the gains are changing all over the place without a person even touching the unit. So we have to deal with filtering and isolation for things like that. A component as simple as a switch is a physical component, so it's not perfect. There's a chunk of metal moving around inside it, flapping around from one contact to another, and it's never a clean transition from low to high. This is a admittedly particularly bad oscilloscope trace from a switch bouncing around. It's moved from closed to open, and it's then flapping around for ages. That might be spending some time in that kind of no man's land between TTL levels. We have to find a way of differentiating between quick button presses and absolute mess coming from a switch like this, so we don't get false presses. We need to deal with immunity from static discharges as well. This is just something as simple as we will end up being the easiest path to ground for some highly charged object near the product at some point. Maybe it's a customer's finger after they've run across the carpet while they were rubbing a balloon on their head or something like that. They bring their finger towards the on button, and there's a discharge of a few kilovolts to the unit. It zaps across the PCB, and there's a voltage spike that comes up next to the microcontroller while it's turning on. Maybe it flips a bit in a peripheral register that we never expected to flip. Maybe it moves the program counter even. It can manifest in all kinds of weird ways. So we can't plan for it that much. We have to test for it. We can use this ESD simulated gun. That's really fun. Zap a few kilovolts through the product, see what happens. And there's regulations that set benchmarks that we have to meet there as well of how many kilovolts we can tolerate a discharge before the customer has to get involved and do something to get the unit functioning again. Most of the mitigation for this is in hardware, but I bring it up because there's firmware tools that we could use as well. Pretty much every microcontroller has a dedicated watchdog peripheral. This is a timer that we can reset when things are going well and stop that timer timing out. If that timer ever times out, then we know something's gone wrong and we can set what happens with that timer. maybe it just resets the whole system and we start afresh, hopefully without the voltage spike this time. Or maybe if it's a bit more sophisticated, we can kill a thread in the OS and restart just that bit. The microcontroller itself can also be a noise source in the rest of the system. Every time we're crunching numbers, we're doing some work, we're pulling a little bit more current and causing a small voltage fluctuation on the power and ground rails around the microcontroller. If we've got periodic work to do, say in synchronization with the USB frame rate on our audio interfaces, we've got a chunk of work to do. Every time we get a USB frame in, chunk of packets, we have to do a load of work, pull a little more current, and that's periodic. So we end up with a periodic voltage fluctuation around the microcontroller in the audio band. So if we're not careful, that can be conducted across to the audio side of the circuit, and we can hear that. And we can do, obviously, electronics mitigations for that, but there's firmware things too we can do. We can batch things up, we can change the order of processing to try and mitigate that. We can have problems, sometimes our weirdest debug problems have come from the actual debug tools we're using ourselves as well. With the advanced access we get, we're chucking signals around on a temporary bit of the system that we soldered onto a few wires that can be tens, hundreds of megahertz. And it's non-deterministic too. On a Monday, the developer might lay their cable down this way, and then they go and have a coffee and they move it out the way. And then suddenly there's all kinds of problems that were there this morning and have gone away. And it's just because of a debug cable. It was never actually a real problem. It never looks quite as bad as that. And then we have to think about playing nicely with the rest of the world and other people's products as well. We get RF radiation coming out of the unit because we have digital signals knocking around with edges, and those edges have lots of high-frequency content. We don't really intentionally want that, but we have to have it, and some of that ends up radiating outside of the unit, can cause interference with other people's products, or even our products too. So we have to test for this again. We can't really do this in the office. We take the product down to a semi-anechoic chamber like that, stick a big antenna in front of it, see where it's radiating. Often this radiation can be quite directional, so it can be easy to miss as well, particularly with the long, thin things like a keyboard. You can find it's absolutely screaming out at the end of it, but when you look in front of it, it's absolutely fine. And most of that is hardware mitigation, but again, there's things that we can do. We can look at the pinout that we chose early on with the electronics engineer, and we try and plan for that so we don't have to make changes to this later on. That can help us to keep sensitive signals on long traces away from aggressive signals that are going to cause the noise problems. We can look at how hard we're driving signals. There's a trick we can pull out in some microcontrollers called spectrum spreading, where we can modulate the core clock of the microcontroller just a little bit, and that helps us to bring that peak down and spread it over an area of the spectrum, so the energy is spread out over some frequencies. Not every microcontroller supports that, and when we do that, we have to be careful then that we don't mess up clocks that we need to be more stable, like audio clocks and USB, so it increases the complexity too. If we think about the features that we actually deliberately put in the product, like USB and MIDI, we can generally lean on standards to give some confidence in compatibility with other people's products there. But the focus always has to be on what the user's trying to get out of the product. And sometimes those standards fit the bill perfectly, and we stick to them like glue. Sometimes we find ourselves needing to creep just a little bit outside of the standard, or maybe we're adopting a new standard that we know not all of our customers have host PCs that support. So we have to look at what the user experience is going to be like for the majority of people and those edge cases, and find pragmatic solutions. Sometimes we will depart from the standard a little bit if we think it's going to be okay, but we'll provide fallback features, and then we end up with some more firmware development work to do to provide something like a low power mode on the Scarletts, where the user doesn't just hit a brick wall if the PC can't provide enough power. We find some way of messaging that to the user and giving them some experience so they can get back to normal. When we get that stuff out into the field, we can keep monitoring it. We can see if we actually get fault reports. We can see what the failure rate's actually like in the real world and learn from that for next time. Hopefully next time we start this process again, we've got some data to build our decisions on. Maybe the standards world has moved on slightly as well, and those newer standards that are a bit more capable are more widely adopted. And we keep learning from that and hopefully getting better all the time.
Grand. So, what have we covered on our wild ride? We started off by picking a microcontroller, and we set it up how we needed it. We worked with hardware engineers and software engineers to get everything running nicely together. We demonstrated that it could respond from a huge ESD strike and that it was EMC compatible, standards compliant. Now all that remains is to stick it in a box and send it out into the field. Yeah, like Andy said, what we've talked about today, this represents some of our current processes and our current thinking. We're always trying to learn and trying to develop. It sounds like I need to talk to Ben about bootloader design, certainly. Yeah. Yeah, but it's a lot of fun. If you're interested in it, then Andy and I are going to be around for the rest of the conference. Please give us a shout. Similarly, check out our careers website. We've got some interesting roles available at the moment if you fancy joining us on the ride. Thanks for your time.